This conference will now be
For the
recorded.
starting part, I was working as a design engineer, but for the later part, for last 6 years, I've been working as a stress engineer. So I'll be taking a session, and if you guys can just clear this out, that whether my screen is visible to you guys or not, or everybody can see my screen or not.
Yes, sir. The screen is visible.
Okay. So on the screen, you can see three things: that why Caesar, what we learn in Caesar, and the third part would be the software overview, right? So first of all, why Caesar? Anybody who could like answer this? Why Caesar? Why do we need Caesar? Is it that worth of a software in piping industry? What is the utility?
Caesar is mainly used for piping stress analysis. It's like external software. So as per the code, whether that piping is capable of taking that expansion or in sustained condition, whether it is within that allowable as per the code, whether we are using 31.1 or 31.3 process piping. So for that analysis purpose, Caesar is used. So actually, the main purpose of that Caesar, whatever the stress analysis software is to optimal the design, structural integrity, and minimize the cost.
Minimize the cost. I mean, how come can it minimize the cost? Any example?
Any example? For example, if we are not using supposed any analysis software, we can put a lot of supports. Support may increase the cost of that piping also, cost of that everything. And as per Caesar, as per analysis software, we can remove the unwanted supports also. And whether it will, if we want, it will increase the cost now, sir. Unnecessarily, if you are putting a lot of supports, instead of, for example, I want two supports, if I put 5 to 6 supports, it's unnecessarily increasing the cost of the piping.
So you're
Some of the project
saying
order.
over supporting is the main cause that is increasing the cost of the piping. Okay.
Yes, yes, yes.
But lot of procurement team has an issue. Like procurement is always has an issue with the teaser guys, or say the stress engineers. Why? Because they increase the add-on cost of the project. Now, how do they do this? Is by adding springs and bellows. So the thing which you were talking over here, that you are increasing the cost of the project. Okay. So over supporting, say like how much you'll be maximum, say supporting it's if it's like 22, 25, 50 m-meter line. Okay. So like say if you're using if you are like if your pipe is running say long 50 meters long, so yeah, like using n number of supports, say that let that n be equal to like divided by 5, right? Or you can say even it's 12 number of supports. Okay. Because obviously if anybody who is supporting giving any number of dead supports, anybody who is supporting, who's working on support, so he has that much of logic that he will assume that certain amount of load, okay fine, this is the amount of sustained load. So anybody who's supporting, who's doing the basic supporting on piping, he's keeping that sustained thing in mind, that this particular support, this much of support, say my two supports can support a span length of 4 meters, depending on the size of pipe I'm dealing in. Say if it's a larger size, obviously your span will tend to decrease. Okay. If it is a heavier size, sorry, if it's a smaller size, again at the same time your span might increase, because obviously the and even the size of the members will decrease. Okay, if it is a smaller size. So say you're using an ISMB 500 for like a 12-inch pipe, but say if you're supporting a 4-inch pipe, the same ISMB might be 150. So over supporting, as you were saying, that we are decreasing the cost of the project. So this is, uh, I would say it's not 100% correct. It's slightly correct that yes, you kind of decrease the cost of the project, because if you go into, like, if you're running the plant, and say a certain line is failing, which you think it must be passing, okay, which you practically think that this much of pressure and temperature can actually, I mean, it won't fail my nozzles or my connections. So that thing is avoided. That saves the cost of the project, because if that particular line goes into failure, the cost of the project actually it increases, because again that's your scope and you have to work on it again. So that part is saved. But overall, if you're talking about this thing, it's actually not helping you a lot. Okay. So now, as you said, the first part which you said, that why do we use Caesar, I very much agree with it. Yes, we use Caesar just to get your sustained loads. By sustained, basically, I'll explain later on what is sustained load, what is expansion, what is operating load. So simply we use this. You use Caesar in order to get the loads. Now, loads would be basically categorized into three categories. One would be because of the dead weight. What do you mean by dead weight over here? Simply, dead weight means that whatever is the weight of the pipe, say this is my pipe, it is having some insulation over it, and let's say it's a 12-inch pipe, and it is having some insulation, an insulation of say 60 thick. Okay, and plus it would be around say 40 schedule line. Let's assume it to be 40s. Okay, this schedule. And the next thing would be the material. Okay, every material has its own density, so depending on that, there would be the certain weight of the pipe, that this is the weight of the pipe. So that weight plus your pressure, that gives your sustained load. So now, when I was talking earlier that when a particular engineer, or say a particular designer, a pipe support engineer, or might be like a pipe design engineer, okay, when he is installing the supports, when he's saying that I got to use this n number of supports in my pipe, what he's actually looking at, he's looking at this criteria, that sustained. This is the amount of load that I require. Sorry, this is the amount of support that I require in order to clear my pipe in case of sustained load. But when you come to a Caesar guy and you say that, okay, I've used these number of supports and my loads, I guess this will work. But he will say that this is what you have done only for sustained. How about for the expansion and the operating case? How about for this too? Because when you're talking about your expansion and your operating case, there are very two important things that are being compromised in case of sustained load, because in sustained only you're talking about that your pipe is filled with whatever fluid, your pipe is having that insulation, and it's resting on a support bed, and you have only assumed that particular scenario, but you haven't assumed for the temperature, which is a very critical factor in any case. So whatever be your temperature, based on the temperature, that particular pipe would be having some expansion, right? That pipe would be having some expansion. Now this expansion thing is very critical. Now why do we say this is very critical? Because obviously any expansion in any direction would add stress to the other end of the pipe. Now what do I mean by this? Say this is the nozzle of my equipment. It's like, say this is my equipment and I got a nozzle over here. Say this pipe is traveling somewhere like this and it's getting connected to some other equipment over here. Now let's not be very practical about the piping, because this looks very odd. This is just an example. Let's not take this serious. Okay, so now when I'm talking that this particular line is going in this direction, then it's coming down and getting connected to another piping. So the temperature for this line, let's assume it's 400 degrees Celsius. Now when at this temperature, this material of the pipe, let's say it's SS316L, this material will have certain amount of expansion. Now when this will expand either in this direction or in this direction, obviously because these 2 points are fixed. Now when these 2 points are fixed, the pipe will only move in the other direction because it can't move in this direction. If it moves in this direction, this will actually hurt your nozzle over here, which would be the point of failure and the point of concern where we get the nozzle loads for. Always when a vendor gives a nozzle load, it is always for this particular point, this point. Okay, so it is always for this point. So now when we are talking about the nozzle loads, so as I said, it is always for this point. Now say it's a 400 degrees Celsius line, it will expand in this direction, this will expand in this direction. Now what would be the movement, the actual, like say the practical movement of the pipe would be something of this sort. Okay, it would move somewhat this way. I mean the displacement might not be that big, how it's looking. You can say it's a bit like magnified view. Okay, in order to just get a clear idea, clear picture of the movement. So I have increased the scale of my deflection. So now what is happening? That the movement of this pipe in this direction, it is actually pulling my nozzle. Now when it is also pulling my nozzle, it is causing some stress in this area. And then again the same case over here. So these two areas are again affected by the movement. So movement in either direction, say this ways or this ways, it will impact my piping. So that is why we always say that any pipe where the temperature, we classify certain degree, we classify certain criteria in the piping design basis itself, which is the design basis or the criteria for a stress engineer for each and every particular project. Or say it might be company static. Okay, it might be like say a particular company who does any project, they keep this as a criteria. Like what we basically do, we keep it as 90 degree. Any line which is above 90 degrees Celsius, the operating temperature of the line is above 90 degrees Celsius, we keep it for stress analysis. So this is one of the general criteria we do follow. It might be different from company to company, but 10 or 20 degrees Celsius, it might be like plus or minus any ways. It might be differing each way, either side. So this is how we basically classify our systems, that okay, these particular lines are going to come into our stress analysis criteria. Now this is how we proceed. If anybody has a question over here till now, you guys can please come up.
Yes, sir. Actually, I am having one question. In 31.1 only, that span table will be there, and table 121.5. Where if I'm using in 31.3 process piping, there is no span table will be there. So at the time, what I can do, how I can able to support, because sustain stage is normally dead weight of the pipe. Even
Exactly.
that table 121.5, they are mentioned 2.5 mm. We have to minimize its displacement. That is the sag. But in table 31.3, there is no such a constraint will be there. There is no such a things will be there. For example, how much you have to maintain the sustained sag, because obviously in sustained condition, if I want to see in stress analysis, if I am doing, first I want to see that displacement I have to be controlled within 2.5 mm. Then only the pipe will be sitting on that support. Otherwise, it will be not useful for anything. So first step is I need to control the displacement. For that, anything is there in 31.3, especially I'm asking.
So, like, if I got you clear, so I would just clarify one thing over here. That is, you were asking point number one is how to calculate the span, right?
Yes, yes, sir.
How to calculate the span. This was your one point. Second was your, like, if my pipe is lifting up, okay, there might be two conditions. One is lift up, and say the other one is it's coming down. Okay, sagging condition, you're saying my pipe is sagging. Okay, so sagging, obviously, when we all might be through with this term, what does sagging means? Say this is my support and this is my line. So what is actually happening? Like, my line is behaving some ways of this sort. Again, it's a magnified view. Let's not take it to be that serious. So here, what he is saying, what my friend is saying, it's like 2.5 mm. This has to be below 2.5 mm in order to say my supports or my supporting is correct. Yes, you're 100% correct. This has to be below 2.5. In case that, say, there are like two supports, and when we are seeing the deflection of the pipe, so it should not go this way. The deflection should not go this way. So how would we get it? Now in Caesar, whenever this sort of situation happens, so Caesar basically prescribes the ratios in case of sustained, and Caesar also gives you the displacement values for the pipe. So you get the maximum displacement in case of say this thing, the pipe, wherever the pipe is falling down, you get the maximum displacement. And if it's a problem, if say it's above 2.5 mm or it's even at 2.5 mm, you can shift your support always. That is why I said a piping design engineer, he thinks that, okay, fine, whatever loads I have placed, that are absolutely okay, but that might not be the case, because whatever standards we are referring to for calculation of span, or say like whatever standards we are referring to where there is certain criteria that say if your line is 4-inch and your material is austenitic steel and your temperature is this much, so the supports have to be between this to this. Okay, but what very important value that has been ignored, or rather that is not pragmatic, that is your density. Because say if you are using a denser medium compared to water, if you are using a denser medium, say if you're using a crude is a very heavy fuel. Now if you're using crude, your span, it goes on in your span basically it decreases. When you're using crude, your span will decrease because you got to support your pipe much more closer compared to what you were supporting, what you were using the same supports for your pipes, which were carrying fluid which is with of a comparable density to water. So that is what is the case over here. Now span calculation, it has certain formula. Basically it has certain formula for calculation of span. We'll be telling you that formula, but again that formula does not consist of density. So again it will create some issues for you. Okay, so basically what we have for you is Caesar, that will give you the exact results that where you're supposed to place your supports in order to pass in sustained as well as in operating conditions. Now the other thing he was saying, if there is a case of lift up, say my pipe is actually not resting on the supports, he would use this one word that my pipe is not resting on the support. So all these things are they are different. They are different scenarios, but we are clubbing them all together and letting you know. Okay. So now when there's a condition of lift up, so lift up has a lot of conditions again into it. One, when is your pipe operating and then it is lifting up from the support? Okay, it's a different condition. In operating case, when there's a lift up, it's a different condition. If there's a lift up in sustained condition, then you cannot help the cause. Either you put a vertical down support. Okay, either you kind of clamp it or do something in order to restrict that lift up in case of sustained loads. I'm all talking with respect to Caesar. So when there is a lift up of say 2.5 mm, 2 mm in sustained case, so always this is not permitted. Any lift up in case of sustained, this is not permitted at all. Any lift up above 2 mm or 2.5 mm, it is 100% not permitted. So you cannot assume this. Now, in order to curtail that lift up, what you're going to do? You're going to put a hold down support. Now, if you're going to use a hold down support, what will that do? It will increase the stress in the line, right? So whenever you're having a condition where there's a lift up in sustained case, what we basically do is we use a spring because we don't have any other option. Whenever there's a lift up in case of sustained case, always remember the case is very particular. Whenever there's a lift up in sustained case, we always use a spring, because if say there is no area where we can increase our stress, obviously if it is permissible, if it is within the permissible limits, obviously you can increase the stress and you can put a hold down support and like whatever you want to do with the line. But say if your line is not permitting that, you're supposed to use a hold down support over here and increase the stress in the line, the only option left for you is springs. So you will only use springs for that. Okay. And once again, calculation of the span will be providing you the formulas. Obviously you can cross check, like whatever particular span length you're giving, or whatever span you're assuming for the line, is that correct or not? You can always cross check with the formula. It will always be on a conservative side, whatever Caesar is doing and whatever you are calculating. So that is why we have Caesar. That is why even the sustained loads, whatever supporting the design engineer is doing, that also we as stress engineers, we do not believe in his supporting. Simply saying, it might be a bitter truth, but we actually do not believe in whatever the piping design engineer is supporting. It might be whatever X years of experience he is having, but we always stress on this point that any line which is of a size over 8 inches, we always take that line in our scope. Okay, I'll just give you the list of criterias, that what are the criterias for basically classifying a line into a stress system line, that this particular line might be prone to stress. So there are n number of criteria. Okay, I'll let you know those criteria. Let's now switch to operating. So is your doubt clear over here, like whatever you were asking about
Yes,
the
sir. Yes.
span, lift up and sagging? I hope it's 100%
Yes.
clear. Okay.
Yes.
Any other person who's having any doubt regarding this?
Yes, sir. Hello.
Please.
Yeah, actually, I was talking about the density part, which you talked about. We don't take okay, while calculating the span, we don't take the density into effect. Just like
Hmm.
crude, if we are taking something having more denser than the water. Okay.
Hmm.
So
Hmm.
my
Hmm.
question is, prior to be having Caesar,
Hmm.
so you are also doing the stress analysis, right?
Hmm. 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 Hmm.
In case of that stage, what they were actually doing to mitigate this effect, like if we are not taking the
Uh,
density when calculating the span.
yes, that was like say they were very conservative. Like obviously, then they were all based on the practical experiences that they were having. Because obviously anything that is, say, like somebody observed that a line of this particular size, this particular density, this particular temperature and pressure, it is failing at this criteria, this is this value. Okay, say if somebody hasn't derived a formula, oh sorry, even if the formula has already been derived for span, but they're calculating and placing at the same particular distance, and still the pipe is failing, obviously they learn from the past mistakes, and then somebody will come up and say that, listen boy, we have used this particular span calculation formula and still the pipes were failing, so why not to use a conservative value? Why to still go with the same values that we're using in the formula? Why not to use this, that, like, say if the formula is suggesting that the span has to be 10 meter for this size of the line, like say it's a 4-inch line, and my span is suggesting me that it has to be the span between the two supports has to be around, say, 7.5 meter as per the calculation of the the formula. So if I go with a conservative approach and I say that instead of using 7.5, why don't you better use 6, or use 7, oh sorry, or use 5.5? So then it came, okay, fine, instead of using those big gaps, we can just minimize the gap and go with a conservative approach. And like if it adds on certain number of value to the project, and at the same time we are minimizing the criticality of the plant, so it's better that we go for this approach. So that is why they went, I guess they went with this approach, because whatever I have discussed with the EIL team, so they have always suggested this. Even if you look at the isometric diagrams, they have all drawn those diagrams like 20 to 25 years back. They've all similar what they have. So yes, this is like, even right now when we're doing Caesar, most of the time we are going with a conservative approach. Say if we are analyzing a nozzle for a particular equipment, we are going with a conservative approach, like make that particular nozzle much more fixed. So if we are using, if you are actually saving that nozzle in a far serious situation, then obviously we can save that nozzle in a better climatic, better scenario also, which it might be prone to. Like say there might be a certain nozzle is fixed on an equipment, it will be having certain number of flexibility. But say if I'm decreasing that flexibility from that nozzle, I'm taking out that flexibility from that nozzle, and I'm saying that my nozzle is very stiff. So if my nozzle is very stiff, the amount of stress that it is going to be bear, it is going to be tremendously huge. So if I'm saving my nozzle in that particular condition, then obviously if it is in the actual world, when it is prone to a much more flexible condition, it will be behaving in a better manner. So whatever work I'm doing, I can be much more confident with it. So obviously, nobody is, like say, nobody is sure about this, about whatever he is doing. So it's always better to go with a conservative approach rather than going with, like say, if I'm having say a certain value, if I'm having a yield of 60 ksi, okay, if I'm having a yield of 60 ksi, I cannot go and save my line with 59.5 ksi and say the line is safe. Okay, boss, I have done the work. Because I'm having 99% value, I have to keep certain margin in order to save my work. So that is what how they went forward. Okay, now
Exactly.
quickly I'll just explain one more thing over here. One is the operating condition, what is operating, and the next is expansion. Okay, so operating is basically your W plus T plus P, whereas your sustained, I didn't tell you, like I might have told you, but I haven't told you about this thing, the load case. So your sustained is W plus P. W is the dead weight of your line. Now dead weight, I guess everybody must be familiar with this term. What does dead weight means? And pressure is like whatever pressure you're operating your line at. Like say it's a design pressure or be it an operating pressure. Design pressure, sometimes it's also referred as MAOP, MAWP, maximum allowable working pressure. This is also referred to sometimes as this value. So do not be confused with like design or like maximum allowable. So anything, you can use any of these terms. Okay. Next, you go with the W plus T plus P, which is your operating condition. So again, the main thing, that the main culprit which is coming into scenario is your temperature. So your temperature, which is actually coming up with a case so called as expansion. Expansion is basically your stresses due to your pure temperature case. So it is all your pure temperature which is actually impacting the line. So these are the three conditions, the basic three conditions that first of all you should know. Then comes your occasional cases. Occasional cases, you basically, it comprises of like occasional, and as itself, it's like occasional. I mean, it can occur once in a lifetime. It can also occur multiple times in a lifetime. Say it won't occur on a daily basis, or it also might be on a daily basis, because occasional also consists of PSVs. Okay, so PSVs obviously they can pop up daily. Okay, or they even can't. So this is certain. Your PSVs come into occasional cases, your seismic loads come into occasional cases, your wind analysis comes into occasional cases, your like you can say ice, or like what you can say, ice fall, snowfall rather, your snowfall comes into the occasional cases. So all these are your occasional cases that also you have to incur. But the first thing which you should be very very clear is your sustained operating and expansion. These are the three pillars that you should actually be able to understand, that how am I supposed to play with my guides, which we always use these terms, that play with the guides. Okay, simply playing with the guides means either like placing a guide over here. If it is not working at the particular spot, you're changing the location, you're placing it somewhere else. So in order to control your moment and the displacement of your pipe, moment, not movement. Movement, I'm
Anurag,
using
one question.
moment.
Hello.
Yeah.
Anu, what about negative pressure? If I have negative pressure, then can I feed it in sustained?
Obviously, in case of vacuum, say if you're having a case of vacuum, yes, you can also use that. Say if you're having a negative pressure also, and you're having a positive pressure also, so you can basically make two design cases. Those are like, one would be for your, say, a positive pressure, and the other one would be for your negative pressure. Same goes with the temperature also. In case, say, your line is susceptible to snowfalls or all, like if you're not giving any steam tracing in the line, or your fluid tends to change the temperature and fall below certain amount of range, so you can again make two different cases in case of temperature also, two design cases basically. Okay, so this is this. Now I guess we all might be very much clear over here that how we are supposed to uh, do this, and what are the different scenarios that we are observing. Now we are coming to like how we are going to save our system if it is failing. Okay, if it is failing, basically, say how we are going to save the system. So again, saving the system, you have certain options. One is your spring, the other one is your expansion joint, or say expansion joint, or it's a bellow. You also call it a bellow. Why bellow? Because you're using convolutions over here. Now this convolution has got altogether a different philosophy. Like it's a very detailed lecture, so we'll be doing it some days later on, because it's a complete different thesis. How you're using it, how you need to control the number of convolutions, how you're supposed to apply it in your system, how you're supposed to calculate the number of plies you're using in each and every convolution, and like how you're supposed to control the stiffness values of your bellows, because bellows are having certain stiffness values. So how you supposed to decrease the stiffness values? Obviously, if you're decreasing the stiffness values, the stresses will decrease, and at the same time, if you're increasing the stiffness values, the stress in the system will increase. So it's directly proportional. So that is completely a different thing. Okay, it's a detailed lecture. We'll discuss it some other days. Now coming to spring and expansion joint. So these are one of the two go-to things when a particular line is not getting saved. Okay, if it is not getting, if it is not coming within a safer limit, say whatever the allowable uh, permitted by the stress engineer might be. Okay, next is one of the other thing, that is your expansion loop. So at times we are also using expansion loops in this, that say I'm using a 6 elbow loop or a 4 elbow loop. This can also be used, but this is always used in case where we are having a very long axial span. Okay, axial span can not only be horizontal, it can be vertical also. So it can be in both the directions, in horizontal as well as in the vertical direction. So you can use a loop in both the directions. Now the calculation of the size of the loop, again, it's a complete thesis. Okay, we'll provide you the complete material later on. So how you will calculate the spool, oh sorry, how you will calculate the span of the loop, how will be the size of the loop, and which is the best side of the loop. Because say if you're using a pipe of say 36 inches, so then the loop calculation becomes a total different job. Okay, because the elbows, the 1.5D elbows you're using, in itself it's a huge gap to fill. So what should be the exact amount of spool you're using, and again how you're supposed to support that particular loop, it's completely different. So that is a different chapter, loops. So these are the three go-to instruments for a stress engineer, that if my line is not failing, these are the things I'm supposed to use: a spring, a expansion joint, and a loop. And how you're supposed to use that, we'll let you know. Okay, next comes your other things that we are going to teach are your systems, say your transfer line system, your pump system, how you will model that, how you will model your 1+1 pump system, how you'll model your compressors, how you'll model your lines connected to turbine, heat exchangers, all those things, how you'll model all these. So this is the list of things that we will let you know. Completely just letting you know in brief what we are basically going to explain to you is, this is what we are going to share to you. I'll just provide you the list of things. So first is the basic pipe stress analysis that we'll be doing for certain number of days, say for like 12 lectures most probably we'll be doing this. That is the basic pipe stress analysis. Now what does this comprise of? This comprises of your basic theory. What is your primary and secondary stress? So primary is your sustained and your secondary is the expansion thing. So primary and secondary stress, what is it, how we are supposed to control, and how we are supposed to make the critical line list. That is the third thing, preparing stress critical line list. Then the stress systems, how you're supposed to prepare the stress system, because again once you have finalized your line, you're supposed to make systems out of it. Any number of line that you're choosing, that yes, this needs to be say this has to be analyzed. So any line which is connected to that line, that will also be taken into consideration. Or say any line which is connected to a rotary equipment, that is also supposed to be taken into consideration. And third thing, any line which is above 8 inches, that above or even sometimes equal to 8 inches, that has to be again considered. Because as I said, sustained is a very important criteria. So 6 inches, 4 inches, it doesn't bothers you much. But any line which is equal to or above 8 inches, that starts bothering you when you come into sustained case. So again, you have to consider those lines. So how you will prepare that systems and each and everything, modeling of the piping system, editing the model, combining the piping systems. Again, combining your piping systems is a very, say, it's a very critical thing, Because say if you're having certain battery limit to it, if you're having certain battery limit for your job and the header is outside the battery limit, now how to get the growth of the header into your system? Because obviously the header also might be having some amount of growth, some amount of axial as well as your horizontal growth. Okay, so that has to be taken into the system. So how you will be taking it, how you'll be combining those outside battery limit lines, that will be letting you know. And the load cases, so please, okay, is somebody, has somebody switched on the mic? If you could just please mute yourself. Thank you. Just give me a sec. Okay, I guess everybody is muted except me. Okay, so okay. So next goes your load case combination. So again, you're preparing your load cases, how you'll be doing it, because load cases, they have certain specific criteria that where your certain say your certain load case has to come, whether it has to come above sustained load case, whether it has to come above below your operating case, above your expansion case, and how you'll be making it. Because say when you're designing your springs, so springs, they have a very critical thing that is called as the lock pin arrangement. So you have to give the exact lock pin arrangement to your systems also. So how you'll be doing that, how you'll be giving that lock pin arrangement to your load cases, so they behave so that when it is operating, then your spring is acting, but when it is in sustained case, it is actually behaving like a rigid support. So it has to behave that way. I hope you got me. By lock pin, basically I'll explain you, because in springs what it happens, that spring, they have a lock pin. When they come to the site, they are placed below the line. They, when the pipe is resting on it, okay, the pipe is not in operation. Say it's like it just pipe has just been installed, and the stress engineer has recommended that there has to be a spring at this particular amount of span from any n number of point. Okay, say it's whether it's from an elbow, whether it's from some nearby support, and he has recommended this, that there has to be some spring at this particular location. Now when you come to this particular location and you say that, okay, fine, I have to place a spring, the stress engineer, he recommends that this has to be the hot load, this has to be the cold load, this has to be the spring constant, whatever n number of things he's recommending to you. He's prepared a data sheet, you have sent it to the your vendor, the vendor has sent you the required spring with the required spring constant, and you have placed it below the line. You haven't switched on the line is not in operating condition, it is not being commissioned. So now when you're placing it below the line, so what you are basically assuming that I'm placing it below the line, and my line is not in operation case, so obviously it will be acting, it should act like a dead support. Okay, so basically what is happening, that particular spring in sustained case, that will be a sustained case, because the line obviously would be having the insulation in each and everything. Okay, so your line must be behaving like a rigid, your spring support must be behaving like a rigid support in case of your sustained case. So that lock pin, basically it helps the particular spring to behave like a rigid support when it is actually not operational. When the line is in operational case, what will tend to happen, either the line will tend to move downwards or it will tend to move upwards. So accordingly, the lock pin has to be removed, and in certain number of hours, your spring, it will accustom itself to the movement of the line. So that is why we place a spring. Because say if you're placing a rigid support will be like a stubborn child. He will say that no, I will not move, I cannot move upside, I cannot move downside. Okay, so rigid support is sort of that kid. Okay, he's sort of that stubborn kid who will actually not follow your orders. So, but whereas a spring is that certain little innocent child whom you say, okay, you're supposed to do this, you're supposed to do that, you're supposed to move like this. It will actually follow the orders of the line, and it will actually align itself according to the movement of the line without increasing the stress in the line and acting like a support in the line. So that is why we place a spring rather than placing a rigid support. At times it is required that we are supposed to place a rigid support below the line. We are supposed to place a support below the line, but actually it cannot be a rigid support. So then we call the spring, because we always believe that spring is that innocent child who will actually serve our job, serve our requirement, but he will actually even help us by not increasing the stress in the line. So then is when we call that spring guy, and uh, and he does the job. So uh, let's not get into that first. So basically, coming back to this thing, so load case and everything that has to be told by me, that okay, fine, this is how you'll like design the particular load case for say your occasional loads, your operating, your sustain, your expansion, and hangers and all, each and everything. Okay, so everything has to be taken care. Now next goes your supporting of piping system. Obviously, supporting of piping system, and to really analyze, like, if I'm giving certain support to the line, what will this kind of support behave, whether it will behave like kind of a hold down, whether it will behave like a guide, whether it will only behave like a resting support, or say it will behave like an axial limit stop, how it will behave, whether it will behave like a rod support for my line. So I have to actually get into this thing deep, that any amount of support, any type of support which I'm giving to the line, how is it actually getting in, how is it actually behaving to my line. So that has to be understood by me well, that the design support standards, whatever support standards I'm having, any support, say if it is a shoe support with the guides, with the clamps, whatever it is, how will it behave in my line, how what kind of, so say if I'm giving a hold down support plus a guide plus a resting support, what is this particular support going to be represented as in case of my support standard. So that has to be understood. Okay, then only you can say, okay, I'm supposed to use this particular standard, I'm supposed to use this particular standard for this support, I'm supposed to use this particular standard for this particular support. Then only you can like recommend anybody, if you actually know that, okay, I've supported this, if I'm giving this number of gap in my clamp, so which kind of support I'm supposed to use, which support type kind of support standard I'm supposed to use. Okay, support standard has certain number of leaves to it. Okay, that this particular support page has this support, this type of support, this type of support, this type of support. So actually you should understand which type of support is you're coordinating with in your Caesar as well as in your support system, support standard. So that has to be understood well. Now sustained and expansion stresses, design codes, yes, this is very important, because see, b31 specifies it specifies each and everything. It specifies what your formula has to be, it specifies what your sustained how your sustained load is calculated, how your operating load is calculated. It justifies each and everything, it shows each and everything over there. But when you come to B31.3, 4 and 1, 8, 9, whatever, so you must have heard this question, like if any of my friends who might be having an experience as a stress engineer might be, so if might be somebody might be having in this, so he must have seen this thing, that say whenever we are going for an interview, this is a very common question, that what is the difference between the kind of between the this thing, the codes we are using, what is the difference. It's a very common question, that if if you're into stress, what kind of difference do you feel when you're using B31.3 when you're using B31.1, 4, 8, whatever standards you're using. So now the answer to this is very simple. This is basically your allowables, the allowables that has been defined for these 3 to 4, 8 different codes. Okay, they all are different. The allowables change with the type of code that we're using. So again, the formula and each and everything that has to be prescribed in the standard itself, we will be providing those soft copies for all the things for the complete this package. Okay, whatever B31.1 is saying, whatever B31 is saying, what EJMA is saying, what TEMA is saying, what NEMA is saying, how you will get the loads out of it, and how you will analyze the nozzles in case of your pumps, be it compressors, whatever it is. Okay, will I be explaining you each and everything. So again, your frictional effect, because friction, like again, you know, sometimes what it happens is that due to friction, the normal force that you're getting, like mu into n, that gets you the frictional force. Okay, so the normal force, what it tends to do, your friction, due to the friction force that is coming because of the normal force, it tends to slide the pipe. Okay, obviously, because when you're it's above the limit, it's above the limit, your pipe will tend to slide. So there it's a case where your systems, they don't converge, and there you get the error, and how you're supposed to tackle with that situation, that has to be again told in a separate lecture. Accessing the equipment allowable loads, obviously that has to be understood, because equipment allowable loads, you get the access is a very, very big problem. How you actually tackle with the access of the equipments, and how you actually like import the loads given by the vendor into your system, and see that whether my load is passing or not. But in order to import those loads into your system, the very important thing is the access. The access has to be 100% correctly emulated by you into your system. Then only you can exactly get whether your system is passing or not. Say if if he has given a higher load for your axial system, for your axial load, and he has given a lesser load for the horizontal, okay, or for the horizontal axis, okay, say like whatever be the number. Now when you're importing that particular load, you have messed it up. X goes into y goes into z, and z goes into I don't know what. So then is where that entire analysis comes to zero. So you have to actually understand the axis correctly, that what has to be the axial axis of the line, what has to be the tangential axis of the line, and you have to actually emulate these things good. Okay, so that has to be understood. Now accessing different types and functions of pipe support, as I've told earlier. Designing systems of sustained expansion, again it's the same thing. Pipe rack, pipe modeling, again your loops will be explained. Modeling analysis of the transmission line, yes, we'll be telling you transfer lines basically. Okay, so jacketed riser, again yes, your jacketed line has to be modeled, because it's a very important thing. Most of the lines, what happens is like you have certain cases where your lines are jacketed. So even your exchangers also, sometime say it's a very, very thin exchanger, and you're supposed to analyze that, so there comes the usage of your jacketed line also. So that has to be taken care. Your seismic and your wind loads, as I've told earlier. Analysis, documentation, and each model generation, redesign, and all. So notes to be provided for these topics: theories of failure, concept of stress analysis, support span calculation, and everything. These things would be, you will be provided the complete notes, soft copies of all these things. Now what kind of systems will be designing? One is the storage tank pump system modeling. The other one is the column heat exchanger, and obviously WRC 297 nozzle flexibility analysis. We'll be analyzing all these tanks and tanks and vessels based on WRC 297 nozzle. Okay, so next is your PSV force calculation and your slug force calculation. So obviously PSV, you have two basic calculations. One is where you're discharging the this thing, the whatever extracts you have to the atmosphere in case of steam line. When you're basically discharging it to the atmosphere, then comes your LPG case, or your some line which is hazardous for the environment, and you're actually discharging it into a flare header. So these are two complicated cases, and you have different equations for this calculation of the forces. So that has to be told again. Okay. Then your critical systems like turbine, pump, column, air fin cooler, like basically not the air fin cooler, you can say column, pump, turbine, and might be one more case might be taken. The other one is for reactors. Reactors are your basically very important thing in your complete Caesar this thing, and every plant has a reactor, we know this, right? So spring design and modeling, obviously, and how to like choose a spring from the catalog. Say a vendor has given you a certain catalog and you're supposed to choose like which kind of spring you need, so you have to know how you're supposed to filter out that particular spring from the catalog. Your pump calculation as per API 610, simply it does not mean that complete pump calculation what a rotary engineer is supposed to do, not that part. Obviously your nozzle load calculation, that has to be taken care. Equipment modeling, obviously you'll be modeling all of the equipments, be it like heat exchanger, turbine, how you're supposed to model that equipment, that has to be taken care. Okay, next is your pipe rack Caesar 2 model, obviously your loops, column piping, and then comes your dynamic case. This is important. So dynamic case will be dealing with vibration analysis and your slug flow analysis, where you say it's a hammer load or like you know slug flows and all. Slug flow is basically if you probably if you see slug, we actually do not take like in the Indian projects. I've seen in many projects, many projects, they actually do not take the closing and the opening of the valve that seriously, but it's a very serious problem. Because I'll explain you with a daily example. Say we all are using basically in the North India, we all are using geysers currently. Okay, so geyser, what it is having, it is having a hose pipe connected to that particular nipple thing that is there. If you see in the bathroom, you will see this. Okay, that hose pipe, the moment you are opening or closing the valves, you will see certain kind of jerk in the hose pipe. If you haven't seen or noticed till date, just try to do it now. Okay, hose pipe, why I'm saying, because hose pipe is a flexible connection. Obviously you're like it's a very small load, so your this thing, the other pipes that you're using, be it like PVC pipe or CPVC pipe, that won't show you that amount of deflection, because that is very well connected. So in order to see this thrust force or your slug force, whatever you want to call it, so or your hammer load also, so you will easily be able to see this before your eyes if you close or you open your wall in your bathroom. You will able to see this. You will be clearly able to see the movement in your hose pipe. So you will say that, oh, OMG, like it's a serious movement. It's a serious movement if you just try to notice it. So what I was explaining, in the Indian projects, they are actually, most of the projects, that are actually not taking this into consideration. But the opening and the closing of the valve, it's a very serious problem. Because if you're having certain loop in the line, if it is a very high temperature line, and if you're having a loop in the line, it's a very big problem. Because that loop, once you're closing or opening of your valve, it has a great problem at the elbows. The elbows tend to swing along, so it's a serious problem. So that will be doing in case of the water hammer, and obviously your response spectrum method for seismic analysis. Okay, this is what we'll be covering, the entire thing we'll be doing. Okay, next comes your software. Okay, so software simply will be doing each and everything, obviously how you're supposed to start with the work. Okay, any of the things. Say if I'm starting with a new job, obviously how I'm supposed to, like, say if for example I'm supposed to say I'm supposed to make a new file. Okay, just a demo of the software. so you guys can be a bit comfortable. Okay, so say so this is how you will actually start with the work. You go to new, you make a folder. Okay, like say go to the go to this option, enter the data directory, click over here, make a new folder. I've already made one, so this is my folder. I choose this particular folder, enter the name of the C2 file, whatever the name might be. Say I'm using it as a like demo version, you can say this. Okay, this is my C2 file. I've clicked onto it. This is my unit file. So this is what unit I'm using. It is inches pound. Okay, so this is what I'm using. Temperatures I'm using in Fahrenheit. So you can say it's basically your European country standard. Okay, so whatever we are using over here. So okay, and so this is the interface of your Caesar. Okay, so first of all, the kind of input that you're supposed to require, that you are required, is which standard you're supposed to work on. It has a good list of standards that you'll be working on. Okay, next is your material, which material you're supposed to choose. Okay, so it's like 106 I'm supposed to use. I can use 106. Okay, grade A, grade B, whatever you're supposed to use, you can use it from there. Next is your temperature. What is the line, what is the temperature of the line? Okay, now what has to be the temperature? That is obviously decided by the process team, and whatever the process team is suggesting for whatever line it is. So you're supposed to install that over here, and say I'm assuming it to be like 200 degrees Celsius as the design temperature, 150 degrees Celsius as the operating. Okay, and same goes for pressure also. So pressure I'm assuming it to be 15. Okay, it's pound psi. So let's say I'm using it to be 150 psi, and it's like 100 psi. Okay, so next thing, you've got the material, you've got the temperature, pressure. Next is the fluid density. What has to be the fluid density? But before entering all these things, you're supposed to check the unit of whatever data you're entering. You're supposed to check the unit of it. So what is the unit of it? The unit is pound per cubic inch. Okay, so it has to be properly converted by you. If it is in some other unit, okay, if it is in some other unit, say it is kg per meter square per meter cube. Okay, so the density has to be properly converted into pound per cubic inch. Okay, and then it has to be fed into it. Okay, so the density has to be filled up. Say for example, we are taking it to be around 600. Let's say it's an NC fluid, and we have taken it to be this as the density. Then comes the size of the pipe. What is the size of the pipe? So you have two ways of basically modeling. One is you can model the equipment, and then you can model the pipe. Okay, the other one is you can get the displacement of the nozzle, displacement of the nozzle from the vendor. I can calculate it by using some Excel sheet, or you can ask the same from the if you're having an in-house static department, you can ask the displacement at the nozzle, and you can enter the displacement at the nozzle, and then you can model your pipe. So both the things are same. It's like you can do either ways. If you want to model the equipment and then proceed on, it's your wish. If you can get the displacement, that is another good thing. So you can get the displacement from your team, and then you can just start with the modeling of your pipe. So but like what we'll tell you both the things. We'll tell you how to model the equipment also, and how to like insert place the displacement of the nozzle, and then proceed with the job. Okay, so say I'm proceeding with this thing. I've taken my y-axis as vertical, and z and x as like the horizontal axes. Okay, this is my north. Obviously the north has to be taken care first of all. Whether my north is in this direction or it is in some other direction. Say my north is in some other direction, I have to accordingly fix. If it is in this direction, I have to fix in this direction. If it is in this direction, I have to fix again in this direction. Okay. Mm. Okay. So say my north is in this direction because most of the ISOs are in this ways, are in this direction, and Y is the vertical because we are using Y as vertical. Okay. So once you enter the material, you get the yield and your elastic modulus. So you do not need to bother about it. The Poisson ratio also comes along. Okay. So all the material data is fed into it from the beginning. But FRPs and all, if you're using FRP, you have to actually get the values from the vendor or like from the process team, and then only you can fabricate your own material. Yes, this is possible. You can fabricate your own material, but you have to get the details of the material from your process team or the vendor in order to get the exact value. Okay, now the corrosion and everything, like since it's like 106, or you can give a corrosion also over here. Now weld factor, again, like if you want to take it 1, this is good. If you want to take it 0.8, again this has to be entered, but this has to be entered in the configuration file. Okay, so that has to be, again, it's a like different scope, so we'll tell this to you later on. Say I'm choosing 12-inch as the pipe size. Now this diameter, whatever diameter you're entering over here, this is not the ID. Remember, this is always the OD. Okay, so whatever diameter you're entering, that is the OD over here. So now the schedule. So for schedule, you can obviously, you don't need to enter it into like or inches. You're supposed to calculate and then enter. No, you're not supposed to enter it that way. You simply, like, say it's a 40s pipe, I'm typing 40s, and the schedule comes automatically. So need not worry about like what is the dimension, what is the value in or inches. Let's not worry about that. Now say I'm designing it, say in north direction. Now you can see my north has again shifted in this direction because that is not fixed. How we do it? Again, we do it in the configuration file. You have to fix the axis and everything in the configuration file, and then you need to come to this file, and then you start modeling. Okay, you have to fix in each everything. What is the unit? What is the, like, whether your Z is vertical, whether your Y is vertical, what are your restraint loads, what are your your stiffness loads, everything, stiffness for the supports. You have to fix all of those. What is the friction, the default friction coefficient? You have to always also fix this value. So everything has to be fixed in the configuration file in itself, and then you come to this file. Okay, so but we are skipping that step right now. We're wrapping it soon. So say we are supposed to design it. Now we're moving like, say, 500 inches. Okay, say in this direction, and then we are coming downwards. For downwards, again, what shortcut you're supposed to use? It's Alt C to move to the next node. Now the default node is, you're taking the nodes by, say, a count of 10. You can say the node increment is by number 10. Okay, if you can even change it. Now why I've taken 10? Because say if I'm supposed to install a support, in between, so that I have certain, I can break it into two. Okay, I'll just show it to you. Okay, and I can even take it as the node increment as 20, 30, 40, whatever you're comfortable with. Okay, say certain people, they have my personal feeling is, like, I use always a multiple of 10. So it's always better that if for nodes I'm using a multiple of 10, and for supports I'm using a multiple of 5. So whatever 5 digit is coming, I'm very clear that my report, wherever it is, 15, 25, 35, wherever it is, so that particular 35 or 45, whatever it is indicating, this particular node point is a node point which is indicating the supports. So the how easier you can make your report to be readable, that is in your hand as a stress engineer. If you're showing your equipment, you can show it with a different node. If you're showing a particular branch, you can show it with a different node. So the more easier you make your report for the reader, the better engineer you are, because efficiency is how you define the definition of an engineer. How efficient an engineer is, the better he is. So that is how you define it. Now coming this thing downwards, this is like say I'm coming downwards by 900 inches. Okay, so this is, now again you're supposed to give the bend. How will you give the bend? This, always the bend has to be given at the, like, not at the trailing this thing, it has to be given at the previous pipe. Okay, always remember when you're giving the bend, it has to be always given at the previous pipe. Say you're supposed to give a bend on this pipe, then that particular bend will always come at the 2 node. Always remember this thing. If you need a bend at this particular pipe, it will always come as at the 2 node. A bend at this pipe will always come at the 2 node. Now why is it so? You can clearly see this, like I've given it a bend. If you click on bend over here, you will see it's the bend is at node number 19 and 18. So these are the 2 points. Okay, if you see the nodes, so 19 and 18 are somewhere over here, the 2 points of your elbows. Okay, so now say if I'm supposed to give a bend over here also, I can give a bend over here. This particular pipe will get elapsed. Next, I'm moving to my next node. This is going in Z direction. Let's say again it's 600. Okay, so this is my node. This is how you will basically draw. Now you're supposed to break it. You can even break it. If you're supposed to insert a flange or anything like that, say if I'm inserting a flange over here, say I'm inserting a flange. Now you go to flange, you press the option, you go to model, you get the shortcut control plus shift plus V. Okay, now if you control plus shift plus V, if you press this, you'll get this particular data sheet. Okay, now you completely choose the flange, whatever flange you're supposed to require, whether it's a 300 rating flange, whatever rating flange it is, and you can completely place it over here. This is a flange, and then again you can go to model, press alt plus C, go to this thing, choose a valve, whatever valve you want to choose. Say I'm choosing glow valve, and then I'm given my valve over here. Again, I've chosen the same option. I'm going to control plus C, oh sorry, alt plus C, control plus shift plus V, and then another flange. This is it. Like if you want to zoom it, I'll just show it. This is your valve. Okay. Now say I want to break my system. Okay. Now I want to break and give a stop over here. Say I want to give a say a 3-way stop over here. You know. So how will I do that? I will simply go to break option. I'll break this node. So 2019 has this default option that whatever point you're getting it right at the center. You do not need to calculate it. Whatever node you will absolutely get it in the middle of the line. So you do not need to calculate this. So this is your node. You simply go to restraints. Now whenever you're clicking on the restraints, it's again at the 2 option. So 25, you get the node. If you want to place an anchor, whatever stop you want to place. Say I'm placing a 3-way stop. Okay, I will use X, whatever is my mu coefficient, 25 again, Y, (25) again, Z. Now if you want to give certain gap in your this thing, the supports, you can give a gap also. Okay, whatever gap you want to give it. Now this is what you have defined. Now what you have defined over here is you have defined P1, because we are supposed to run the system now. Okay, we're supposed to run the system now. You have defined P1, P2, sorry, P1, P2, T1, T2. Your hydro test pressure has not been defined, so we will define that also. We'll take like 1.5 times of a design, the old standard that we use it. Okay, so 225, I guess my calculation is correct. So 225 has been this hydro test pressure. We're supposed to run the system now. Now you will see sustained, operating, and your expansion case. This is the default cases you get. Okay, now what you can see over here, it's the system is failing, right? Hydro test is failing, obviously, because the sustained supports have not been provided. Again, you can see sustained supports have not been provided. That is why your this thing is failing in sustained. You can see this. Now, by what it is failing, you are supposed to look at this thing, like by what is the percentage, what ratio it is failing. So you can see over here, this is failing by a huge margin. This is the number. Okay. Now, say if I'm fixing this, if I'm fixing the two ends, if I'm removing that particular support which I had, say I'm going back to my system. Okay, this is my system. I'm removing this support. Say I'm removing this support. At my anchors, say I'm using anchors over here. At these ends, I'm using anchors. Now, anybody could ask me this thing that I said that whenever you're choosing restraints, this will always come at 2 point. Okay. Now, when we choose a restraint over here, it came at 10. It came at from. Why? Because 2 is this thing, a bend. So obviously, it will not come over here. It will always come at the other end. Caesar has this much of brain, because that you cannot give a support at the this thing. If you're supposed to give a support at bend, obviously you're supposed to use a trunnion or something, okay, or some kind of extension. Then only you can give a support. So it takes that into consideration. Okay, now say I'm using this thing. Okay, now I'm running the system. Now, if anybody could just emulate like what actually can be the movement of the pipe, okay. So your expansion is good. Now your sustained is failing. Why? Because
There is no support.
okay, you need a support somewhere. So that is why it is failing in your hydro test and your sustain. If you look at the percentages, this will be fairly decreased. Earlier it was in lakhs or something. We didn't look at the number because it was high. Okay. So still you can see this. Okay, I guess this is again because of the density we have taken. The density is very high. The density has to be decreased. It is probably because of that. Now, if you decrease the density, that is why I said the unit has to be taken very, very carefully. The unit has to be very precise. If you decrease the density, automatically your sustained will decrease. If I'm taking a density of like 0.6, because this is in PCI, okay. So if I'm taking a density of this 0.6 PCI, so this is completely fine, I guess now. Okay, so your ratios have decreased. Obviously, you need to work on your supports now. You haven't supported your line, so it has to decrease. Oh, sorry, it has to be supported properly. Whenever you're getting such vague numbers, say you're getting any number which is above lakhs or something, the ratio is fairly high, which is kind of impractical. Obviously, that has to be corrected. That has to be corrected. Why? Because the entered value might be somewhere, it might be wrong. So whatever you're seeing over here, this is indicating that at node number 10, whatever code stress you're getting, whatever code stress as per B31.3 you're getting, that is very much above the allowable range. Allowable range suggests that the allowable value has to be somewhere around 16,000. Okay, but whatever you're getting over here, this is fairly high. Okay, so that has to be taken care by you. Now it can be easily controlled by placing a stop or something, or even the density is not correct. I might be still say this because we have not taken the actual data, so it's just a demo run. So, and one more thing, we'll just also look at the deflection, how we are getting. Just see the deflection that we are getting. Now I'll just increase the scale. See, like I'll increase the scale to 100. Okay, this is what you're getting in case of expansion case. Okay, I hope you guys can see it. If not, then please. I guess this is clear. Okay, now why it is failing in these two cases, the sustained and the hydro test case. We'll see to it. You can also clarify your doubts by this. Like if you go to this, if it is failing in hydro test and sustained, so it must be it must be sagging or doing something like that. Okay, so if it is not sagging or doing something, then it's a different case. But yes, this is, wait, let me change the scale. So again, you can see there is complete need of support over here. There is no support, the complete pipe is falling. That is why it is doing this thing. Now if we go back to the system, earlier what we have used, the stop in between, the three-way stop. Now if we place that same stop right now over here, this will completely solve the issue. And the movement that we are seeing, that the complete pipe is collapsing somewhere over here, so that will be completely resolved. Hydro test has been resolved, but still sustained is not working. So sustained again. This is how you're supposed to work on this. It might be somewhere around node number 40. Okay. So this is how you're supposed to work on this. This is how CZ helps you out. That it is increasing. It is showing the amount of this thing and displacement. Like as we have seen earlier, we can see the displacement also. That at which point this particular line is falling down or doing something like that, because of which it is failing. Okay. So we have to also check that. Okay, our vertical axis was dy, so this particular digit is in inches, so the maximum displacement that you get, it is at node number 30. At node number 30 you're getting a displacement of 0.3934. okay, so this is somewhere around 1 inch or something. Oh sorry, you're getting somewhere around 10 mm, I guess. You're getting this displacement might be around 10 mm. If somebody can just calculate and let me know. Okay, so this much amount of 10 mm of displacement is you're getting in downward direction, so which is seriously wrong. You have to correct this. Okay, now how will you correct this? There is no lift up. The only thing that is happening, the pipe is falling downwards because of that support you're having. Okay, so the displacement you're getting at whatever displacement you're getting, basically you're getting in that direction only. So that has to be taken care. Now how will that be taken care? Again, we are going to, this is how we are basically saving the system. This is what I'm telling you. This is how you approach Caesar, that you're getting the failures at whatever point you're getting, and then you're going and saving the system. And this is how your system is basically getting saved. So this is a node number 30. Now I'm supposed to break this at some point, and then you can save it. Or another way how you can do it is like you can shift this particular support somewhere over here. You can shift it somewhere over here so that it can support this pipe also, and it can support this pipe also, because the span is like it is way too much. Okay, the particular span is way too much, so you can support this thing. You can move this support somewhere upwards, and you can install a support over here, not exactly at the elbow, because if you'll install a support at the elbow, this will again hamper the growth of the line. So do not do anything such. Do not ever restrict the movement of the line, because the moment you are restricting the movement of the line, you're actually increasing the stress in the line. So do not ever do this. Now how you will do this, if you kind of decrease this by 1, you're adding an extra 20 that has been removed from there, and then you're inserting it over here. Say I am breaking this line at node number 35, and from node number 30 I'm breaking it at say 10 feet. Yeah, it's fairly near this. We'll still increase it by somewhat, because let's not place it near this thing, because there's always an axial stop over here. So this axial stop will always, it will it will create a problem. So because it will start increasing, like you're installing, it will start acting like you're installing 2 axial stops in a same line, so which is very much wrong. Okay, so it's better we install it somewhere in between. Let's see. Okay, if somebody has some question, they can come up with the questions, and we'll take them one by one. Okay.
Hello, I am having one question. When we are analyzing the first one, what we need to check?
See, first of all, whenever this thing red is indicating this particular sustained loads, they're coming in red, right?
Yes.
So what this red thing is indicating, basically whatever the ratio is, whatever ratio you're getting, that is above the allowable limit. Okay, as you can see, earlier it was 350, now it has come down to 264. Okay, so you have to take care of this thing, that whatever is the allowable limit, basically this complete issue is about the density of the line. Now whatever the fluid density I've entered, it's really heavy. Okay, so that is why we are getting this thing. Now when you come to this, When you see this 264, what is 264? If you calculate 423 to 5.4 divided by 1600, you might be getting somewhere around 2 point something. Okay, 2.64. Now when you multiply that 2.64 by 100, that will give this percentage that you're getting. Okay, so whenever you're seeing anything in red, how you tackle that? First, obviously you have to tackle this thing, that you have to save this. It should not come in red. Your percentages should always be below 90%. Okay, whatever percentage, be it sustained, be it like whatever you're getting, be it expansion, be it operating, whatever percentages you're getting, that percentages have to be below this thing. Okay, below your
Yeah.
allowable, and by
Yes, sir.
90. Okay,
Yeah.
and
Am I?
next what
Can
we'll
I
be
ask one more question, sir?
yeah,
One
yeah,
more question.
let me just
Actually,
come, let me just complete.
okay.
Next, what you'll be looking forward to, next you'll be looking forward to the displacement, that your line is not sagging, or you say one support, the line is not lifting up from that support. Now how you will get to know that thing? See, I have placed a resting support in the horizontal span. Now when that line will be lifting up, say my line is lifting up from particular, say support, how I can check that? If I go to my restraint summary, if that support is not lifting up, if that support is not if that pipe is not lifting up from that support, i will get I will get a particular value. If I don't get a value, that means that support is lifting up. Okay, now see, there is this rigid support plus y. I get a value over here in the y direction. I get this 25,000 pounds, which is a very high value. Okay, 25,000 pounds is a very high value. If you calculate in terms of Newton, this is very high. The loads are very high. Okay, so you have to take this thing. Now, if my pipe, say my pipe is not resting, on this particular support, and then what happens? Then what happens is I won't be getting any value over here. That indicates my pipe is not resting. Now you can also clarify this thing by going on to displacements and checking that my wherever supports I've used, whatever nodes at which I have used my supports. Now that is why I've used a term that I use whenever you're segmenting the nodes, whenever you're cutting the nodes, or whenever you are like you know breaking the nodes, you always break it at node number 20 in multiple of 5. Okay, say the last digit should be 5. So I clearly see out of this entire list, I see that node number 25, node number 35. These are my 2 points where I'm getting the values. Now, if that particular support is resting on the pipe, if that particular pipe is resting on the support, I'm getting a value 0. In y direction, I'm getting a value 0. Over here also, if you check at 25, I'm getting value of 0. So this completely suggests that whatever support I'm using, there is 100% acting as I've desired. There is no movement to and fro in the line. Okay, so this is what I wanted to say. Now the next thing, that 35, it has certain displacement. It has certain displacement in z direction, that is the horizontal direction. It has certain displacement which can again be curtailed by placing a guide, but if you curtail the distance, again it will add on the stress value. So this is how you basically work in Caesar. So you have to look at curtailing the movements which you actually do not want, but at the same time you need not compromise that movement to for your stress. So you have to keep a balance between the two. And same goes for your vibration, that whenever you are arresting the vibrations at the lower frequencies, those vibrations have to be arrested in such a manner that the stress of the system does not increases. Okay, because when your system is vibrating at lower frequencies, what happens? You tend to guide your pipe. Now when you're guiding your pipe, what happens? The moment you guide your pipe, you're actually arresting the movement around, the flexibility. You're actually limiting the flexibility of the pipe. So now when you're limiting the flexibility of the pipe, what happens? The stress in the pipe increases. So you have to look forward to this. It's a marriage between the two opposites. So you have to like kind of uh, compromise, in that situation between the two, the stress and the movement. Okay. Yes. Now everybody can just ask me the questions. And before I take the questions, I'll just tell you one thing, that this complete course will take around 35 to 40 hours. Now, depending on like how much amount of time we are giving for the modeling part, because the more the modeling and the analysis we do, the much the time we are spending in the analysis, obviously, the better we are. So that is what we'll do. Yes. Now everybody can just come up with the questions now.
Actually, I am having one question. For example, I have done a wrong unit conversion. I hope Caesar has having, we can change it, we can able to create our unit conversion file and we can change
Yes.
it.
Yes. Yes. You can do this. You can very much do this. It has an utility. This thing. Can you see this? It has utility over here. Now, if you go to create and review units, you can easily create your own unit, or whatever unit you have used. You can no, you can change the particular unit. You can select your unit file over here. Then you can create your own unit, and obviously you can change the model unit also by clicking on the selecting your models, choosing your units, and then clicking on the OK option. That particular model units will also be changed. Okay. Any other question?
Yes, yes. Actually, I am having one more question.
Okay. Okay.
Whatever you are given anchor and some of the semi anchor like that, so
Mm-hmm.
if for example whatever the support is I given, for example expansion is also clear, the sustain is also very well within the limit. If I
Mm.
whatever the loads is coming, I need to give to my civil designer who is taking care of that load. But if the civil engineer is telling that this load cannot be withstand, for example that support whatever the limit stop in vertical line you are giving some limit stop, that one it
Uh-huh.
is creating huge load. If they,
Mm.
my designer civil engineer is telling no, no, my structural can't withstand that much thing, then how we can rectify it as a stress engineer?
See, obviously, if you're say in the vertical line, if your support, you're talking about the vertical line or horizontal. Basically, you
No,
might
no,
be talking
vertical
about.
line, vertical line. Yeah, limit stop. Because why I asking this question now? You are put at two lines, two end is anchor. Normally,
Mm.
anchor it will arrest all the 6 degree of freedom. Three
Yes,
translation, three rotation, it will arrest.
yes,
So there
yes,
is no
yes.
movement. A pipe will try to expansion and contraction, expansion in that direction. So already pipe is expanding. Limit stop,
Mm.
it will also resist that pipe movement. So there is a
Mm-hmm.
lot of reason to create a huge load. So that is the reason
Mm-hmm.
I asked this question.
Yes, obviously. That is, see, what I have done over here, basically, what the problem we are facing over here is that you have used an anchor. Yes, I very much agree that when you're using an anchor, it will arrest the 6 degrees of freedom and your loads will be tremendously high, which is what we are seeing currently. Okay. And also this thing that if you're seeing at the local this thing, if I didn't knew this, you might have seen the sustained loads or not. Sustained loads might are also very high for the same line. Okay. So whenever you're giving your designer, whenever you're giving a designer, you give them the sustained loads, not your operating loads. Okay. Whenever you're giving
Yes,
a
yes.
designer, you give them the sustained loads. Okay. They'll design the system with the sustained loads. See, if your operating is very much high, okay, compared to your operating by I mean the operating case, not the design case. I'm talking about operating case. Say if your operating case is also way higher than sustained load, then you just try to just confirm them once that whether it is like okay or not. If in case he's not very comfortable with the digits, he's not very comfortable with the digits, he's saying no, I cannot use a heavier member over here because obviously my this thing, my platform will not support me to use this heavier member. Okay. So then you have an option that you need to go back to Caesar. You have to anyways decrease the amount of load that you're getting on the pipe. Obviously you'll increase the number of supports. That is the only option you have. You have to increase the support, or you have to give certain number of flexibility to the line, so that you're actually stress in the line, it actually decreases. Okay. So this is how you can tackle it, because you have to ask to your this thing, the civil person, because civil person obviously he will check in his system that whether he can give this member will go with the load you're giving or not. if that particular member is not going with the load, obviously you cannot like rule him and say that no, I want this thing, because he is very much clear. Because whatever he has assumed, say he's saying that no, I cannot give a member above ISMB 150, because this is a very common problem. This is a very common problem that we piping engineers, we give the load to the civil engineers, that this is what the piping support has to be, that this is what the piping support has to bear the load of. Okay, so now when that particular engineer is working on, and he says, he comes up with a mail and say that listen, this support looks, it's like it's way too huge. So he's very much correct. You're supposed to correct that particular amount of load. No, you have to bother that, or you can ask him that okay, could you just give me like what your limits are, because uh, it's not so that in the entire system somewhere he's using 150, somewhere he's using 75, somewhere he's using 100. So that's evenly distributed, that in which area he's using what kind of member. So you can ask him like, what is the limit load that I can give, the maximum amount of vertical load that I can give on a member. So he'll come up with some number to you, and then you can proceed that okay, fine, I mean, whatever analysis I'm doing, I'm not supposed to increase this number. This is the limit which I'm not supposed to cross. Okay, and the example which we have taken right now, it's not a very much practical example, so let's not go with it. It's fundamentally, it's very like it's not that correct. The density, I'm not very much sure about it. So density, unless and until you're not sure about the fluid, you cannot go with it. Okay, because
Hello,
sustainability
Anurag.
is a very important criteria. Yeah.
Yeah, I have one question. Is that
Hmm.
every time what I was seeing in this line routine you have shown, every
Hmm.
time we have to draw this line, each line, or we have to take that line from the PDMS software or especially for the analysis.
See,
Or
if you're
other
having
thing
CAD
is
work,
that at the initial stage you have told that due to expansion, the nozzle nearby the nozzle there will be the some damage. So in this routine, you don't have shown this type of the thermal issue
no, because we haven't
nearby the
drawn the
node.
nozzle. We haven't drawn the nozzle neck. We haven't drawn the nozzle neck. That is why we're getting very high stresses. That is what I said. That since we are getting very high stress values, that since if you're looking at this very high stress values, that obviously the nozzles also won't be safe, because I have shown you the movement, right? I have also demonstrated it earlier that these two pipes will move in this direction, as I've shown you in the diagram itself. Okay, in the 3D model, I've shown you the displacement, right? That the
Yeah.
pipes are moving in this direction. So now when the pipes are pulling the nozzle, obviously the stress at the nozzle will be higher. Okay, now when the stress at the nozzles will be higher, obviously they'll fail. So the stresses, yes, they are very high, and that is
Okay.
why we have used the limit stop in between. Okay, in order to just just make it not make it a crossover, and say the pipe is not moving way too much in the axial direction. That is why we have used a guide in between, and just to limit that.
Okay. And then every time you have to draw these lines, or you have to extract from somewhere.
See, if there are certain softwares, like if you're having CAD works, okay, you can import the complete 3D model out of it, and you can move on. And if you're not if you're not having CAD works, if you're having PDMS and all, obviously you have to extract the ISOs, and you have to model it yourself,
That's
because it's only certain softwares are compatible with it. Like even pipenet, I guess even pipenet also you can import the systems. But the problem with importing the system is like when you have these rigid parts, say if you're having a valve or something, when you're importing it to your Caesar, what happens, the loads and everything, they're not exactly like compromised with the system. Like say if you want to give certain node numbers to your valves or something, anyways, if you have imported it, you have to change these things. And also another problem which we tackle is the branch connection. If you're giving some branch connection to it, like say a certain engineer is working on, it can be any cycle, like he has drawn it, like he has drawn the header, or might be somebody has drawn the branch connection first and then the header. If you will model it, you will model the header first and then the branch connection in Caesar. Okay, but what happens, because of somebody has modeled this ways in this thing, the other software from where you're importing it. So what happens, the complete sequence is imported. Okay, so the node numbers, the modeling of the node numbers starts from the branch connection and then it comes to the header. So that is a problem. So importing this thing, it cannot be that easy.
Okay,
The node numbers are common.
suppose we have sustainable load, and here in the initial stage at node number 10 and node number 19, suppose there is a support from the bottom, structural support, and in your case it is showing that it is fell, and then your job is to highlight that support is not sufficient enough, and you have to give the more rigid supports, somewhere like anchor or like guide shoe, whatever it may be.
Obviously,
So
obviously.
you are going to design this structural support or anchor or whatever this may be, or you're just highlighting this.
No, what we'll be doing is we will be highlighting the amount, the type of support from the support standard. Okay, the members, the type of members, whether it's SMB, whether it's SMB, whether it's SMC, whether angles, whatever type of members it has to be taken care. That is the work of the civil engineer. We will only give the values that this is the amount of load that we are having. We will only give the amount of load to the civil engineer, that this is the amount of load and this is the type of support that what I require at this particular point. Now the members are to be designed by you, and let me know if the members are failing. That is what we do.
Hello.
Yeah.
Another one case I have seen that line has the pressure up to 205 bar, but its design temperature is only 78 degrees centigrade. Then does this line will come in the stress analysis?
Yes, obviously it has to come stress analysis because it's the criteria for pressure also.
Okay. And one more thing, Anurag, related to the course. Actual on scissor modeling, how many hours we are going to spend? Because out of 40, if our course is designed.
Caesar modeling, it's a very, very easy job. Modeling is no difficult job. You'll finish modeling in 3 days.
Okay.
You will finish modeling in 3 days. It's very easy. It's not like SP3D or PDMS. It's nothing like that you have to spend hours and hours in Caesar. If you'll see the commands, like there are hardly any commands into it. Only what you need to give is the flow of the pipe in X, Y, or Z direction, the amount of bends, and whatever the practical situation is. Whether it's like you're supposed to give the uniform loads, that is a part and parcel. The displacement uniform loads, obviously that is a part and parcel. But the amount of command you have for modeling, there are very few. Okay, so it's not a very tedious job. Modeling is very easy, but yes, it's boring. Modeling is boring, but you have to do it. That is why, like nowadays, what we tend to do is like we can import, if we can import from the software itself, from the 3D software, but it's like you can import it, but it increases the headache of the stress engineers. So that is a problem. And modeling it's like no big issue. The main time that we are supposed to spend is we are supposed to spend in the analysis part. How much time we are giving and analyzing the system, because the movement has to come to us naturally. We are not supposed to look into deflection and see like what will the deflection of this line.
Okay.
We say a serious engineer is one who can look at the line itself, the supports, and he can he can emulate the displacement in his heart, that this is the displacement of that line. That is a true stress engineer. Okay, that this pipe will move in this direction, this node will move in this direction, this is the movement, and same thing will be replicated in Caesar. So that is the level you're supposed to reach as a stress engineer. Yes, anyone question? Anybody else?
There is any option to model metallic hose in the Caesar?
Metallic hose, obviously you need to get the stiffness values. You can model it because you have to use the same option, this thing, by using convolutions. Okay, but you have to get the exact the values from the vendor, or like if you're having some catalog, you have to get that particular value.
Okay.
Only stiffness values is the criteria, because I mean, metallic hose, be it any hose, you have to only get the stiffness values. That is it.
In one shot, how many PCF we can import? If I'm getting from SP3D, my designer, in one shot, how many PCF I can import? Even I know that if I import whatever the line, it will not correctly come. Walls and all, it will not come. How we can do that?
You have to select a particular batch, no? You have to you have to basically select that whatever my system is. See, you have to first of all specify the criteria, that what is my system, what is the system. By system, I think, I mean, you can understand, like say I'm choosing a particular line. Okay, I'm saying that this line has to come into my system, this line has to come into my system. Like say some line from a column to a pump, it's going. Okay, the other line is going to a heat exchanger. Okay, and say there is some branch connection, some other branch connection which is going to some vessel. Okay, now that particular line, that branch connection which is going to some other vessel which is having a temperature of say might be 80 degrees Celsius. Okay, but that has also to be considered in the system. So that complete system can be imported into your this thing, the Caesar. Okay, so now selecting those lines and making one package out of it, and then importing that complete file, the complete PCF into your this thing, that has to be taken care. Okay, so making that complete package, that PCF file, that is some task. And like the engineers, they're doing it easily. You just need to select the lines and create one PCF package, and then you can send it to the C2, the engineer, and he will convert it to a C2 file, and then again he can work on it. Because there's this option, if you see, there's this option over here, interfaces, import PCF. Okay, so you can directly import it. Okay, and you can convert it, whatever PCF file you're having.
Yes, I know that one, but one time, for example, 7100B one line is there, 7200 is there, 7300 is there. Can I select all the 4 lines at a one shot?
Yes.
That's what my question.
You can select. That is what I said. I mean, the complete system has to come into one package. Otherwise, it's no use. You cannot like analyze the lines separately.
Yes.
Okay, somebody else with the doubts and everything, or should we call it off?
Thank you, Mr. Anusha. You have done very good. Actually, some basics we can learn from this also. Thank you
Yeah.
for this presentation. Very nice presentation.
Thank you. Okay, I guess so. Nobody's having any questions. Okay, and if you're having, in case if you're having any question, you can get on to Ritesh. Okay, so like he'll be coordinating you with the man hours and whatever amount of what is the syllabus and everything, so you guys can catch with me later on. Okay, so have a good evening and enjoy the day and stay safe. Thank you everybody.
Thank you.
Thank you.